Here are 10 reaction examples from the last part of chapter 21, or I guess it's the second part of chapter 21. And these all involve alkylation reactions of some sort. So in this first one, we have a non-symmetrical ketone, and we use lithium diisopropylamide, or LDA, and then we alkylate it. And so when we use the LDA here, LDA is going to predominantly give you the so-called kinetic enolate. And then this enolate just acts as a big old nucleophile, and it's going to attack the alkyl halide. And so what we're going to end up with here as a product there's your enolate carbon, and then we're going to add to that 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So we should have a total of 5 carbons there. And then we can contrast this with the next one, where instead of using LDA, we're using sodium hydride. Sodium hydride at room temperature is going to give you more of the thermodynamic enolate. And so that's going to be the more stable enolate as based on the double bond in the other resonance form. And so again, this is just going to act as a big nucleophile and attack that benzyl bromide, and the resulting compound that we're going to get out of this is this one. I don't know why I put that in there. I think I had those other compounds on the brain. The compound that we're going to get out of this is, and I'm just going to abbreviate the benzene ring as pH, or I suppose since I asked you guys to write it out, I should write it out as well. Albeit not very well. And, you know, these alkylation reactions will work with anything, any sort of an alkyl halide that's a suitable SN2 substrate, because this is an SN2 reaction. So we're talking methyl, benzyl, primary, those kinds of things. So the next three concern the malonic ester and the acetoacetic ester syntheses. And here we have a reaction which is named not after a person, not after a product, but actually after a starting material. And so the two featured compounds in these, and they're really the same except for the starting material. So this is diethyl malonate, which is the ester of malonic acid. So that's why this is referred to as the malonic ester synthesis, because this compound here is diethyl malonate. And then we can contrast that with the starting material for the acetoacetic ester synthesis, where instead of having a diester, we have a ketone and an ester. And this particular compound is known as ethyl acetoacetate. So there you go. So what happens here is that the first thing that happens is that the sodium ethoxide is a strong enough base to completely remove the alpha hydrogen that's acidic to these two carbonyls. So that's going to have a substantially lower pKa, and sodium ethoxide is going to be a good enough base to remove that. And so then what happens is that our nucleophile attacks our alkyl halide. And again, this is an SN2 type reaction. So we're looking at SN2 worthy substrates like primary, methyl, benzyl, allyl. And so when we do that, I'll write out this intermediate. And we're going to add to this 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So that gives us that compound. And then the acid and heat do a couple of things. The first thing that happens is that we hydrolyze both esters to the carboxylic acids. And again, we should 1, 2, 3, 4, 5, 6. And so that gives us this compound. And it turns out that a carboxylic acid with a beta carbonyl group, doesn't matter if that carbonyl group is another carboxylic acid or it's a ketone, decarboxylates. In other words, it loses carbon dioxide. And here we have two carboxylic acids. They are effectively the same. So we can just carve out one of them. And the product that we get as a result, and again, I'll write it kind of funky like that. And so what's happened is the new bond that we made initially was here. So this is the piece that came from the alkyl halide, and this is the piece that came from the malonic ester. And so what this synthesis does is it adds CH2CH2 to whatever your alkyl halide is. So here's your alkyl halide, here's your alkyl halide, and we added CH2CO2H. You should be able to understand the mechanism of this reaction, except you're not responsible for this decarboxylation step. You're responsible for being able to recognize compounds that will decarboxylate, but you don't have to write the mechanism. So the same sort of thing happens with the acetoacetic ester synthesis. We make the enolate, and then we alkylate the enolate. And again, sodium ethoxide is a good enough base to make this enolate because the enolate is on a carbon that is alpha to both carbonyls, and we need an oxygen here. And then what happens is this first hydrolyzes to give you that. And then this compound in turn decarboxylates. Now we have two carbonyls. We're going to specifically lose the carboxylic acid one, and I'll try to write this a little neater. And so that gives us that as a product, because let's count carbons. We had 1, 2, 3, 4, 1, 2, oops, wait a minute, something bad happened. 1, 2 carbons between the carbonyl and the 5-membered ring, so we're good to go. And so then this would be the final product. And again, if we kind of pick this apart, here's the piece that came from the alkyl halide. Here's the piece that came from the acetoacetic ester. And what you can see has happened here is that we've added CH2 carbonyl, or an acetyl group, to the alkyl halide. Now, sometimes students ask, why does this decarboxylate? You know, how do we know something's going to decarboxylate? And the key to the decarboxylation is the heat that I forgot to write in. So there would be heat involved here, and as long as there's heat, then you assume that there's going to be decarboxylation. Because we've seen some reactions, so for example, we've seen with the Klein reaction, you get a beta keto ester, and if you were to, we protonate that in the last step. Well, if you protonated that and heated it up, yes, the ester would go to a carboxylic acid and it would decarboxylate. So this one's kind of interesting. So what happens here, and probably should specify that we have an excess of this. So what happens here, I'll draw it in pieces because it usually drives students a little crazy. So the first thing that happens is we make the enolate, and then the enolate attaches to this piece, which has 1, 2, 3, 4 methylenes. 1, 2, 3, 4 methylenes, and a bromine. And then we make the anion there, and this attacks the other end. And so what we're going to get out of this is a ring that has 1, 2, 3, 4, 5 carbons in it. So that gives us that compound. And now when we decarboxylate that, well, hydrolyze and decarboxylate, we're going to lose one of these two carboxylic acid groups, and we'll be left with that compound, plus, of course, CO2. So this is a perfectly legitimate thing to do, to take these compounds and either alkylate them with something that has 2 leaving groups, so you get a cyclic compound, or to do an alkylation with 2 separate compounds, with 2 separate alkyl halides. So that's the malonic ester and the acetoacetic ester syntheses. And again, they work exactly the same way. It's just that the starting material is very slightly different, but everything else about them is the same as the other. So in this next one, we're going to use some reactions from the beginning of the chapter. So when we brominate this in acid, just as a review, this is a symmetrical ketone. I picked that on purpose. And we're only going to add 1 bromine. And the reason why you only get monobromination in acid is that the halogen acts as an electron withdrawing group, makes this oxygen less basic, and therefore less likely to pick up a proton, and that's what has to happen in the rate determining step of this reaction. So now we're going to use this lithium carbonate. Here's a mild base, and we don't need much of a base because we're making an alpha beta unsaturated carbonyl compound here. And these alpha beta unsaturated carbonyl compounds react with weakly basic nucleophiles to do a conjugate addition. If you have a strongly basic nucleophile like a regular enolate or a Grignard, it will do direct addition to the carbonyl. So in other words, I'm going to put this up here. So direct addition is strongly basic nucleophiles, and conjugate addition is weakly basic nucleophiles. And now I've kind of run into the room that I had allotted for this question. Let's see if I can move this up just a scooch to give myself more room. There we go. And then with the note that goes with that page. All right, so what's going to happen here is that these cuprates or Gilman reagents are going to add conjugate. So the copper carbon bond is not as polar as the magnesium carbon bond that you'd have in a Grignard. So these tend to do a conjugate addition. And so the initial product that we're going to get, that was an ethyl group, so the initial product that we get is that. So the nucleophile, which in this case is the ethyl of the Gilman, attacks in the 4 position relative to the oxygen, or the beta position relative to the carbonyl. And we initially get that. And then when you add the acid, 2 things happen. The first thing that happens is that you protonate the oxygen. This is an enol. Enols are not stable relative to the keto form. And so this does an enol keto tautomerization. And I'll move that down for aesthetics. Move that down for aesthetics. And so what we've done is we've managed to alkylate the beta position as opposed to the alpha position. So now we know how to do both. If you go back up and you look at the first 2 reactions here, those were alpha carbon alkylations, which we did by making the enolate. This is an alpha carbon or beta carbon alkylation. And another important difference is that if we go back up here, the alkylating entity is the electrophile, and the enolate is the nucleophile. Whereas if we go back down here, the alkylating entity is the nucleophile, and the alpha beta carbonyl is the electrophile. So this carbon-carbon double bond is acting as an electrophile because of its adjacency to this carbonyl. So when you have this so-called, if you want to use the old terminology, you have this kind of, 1,4 addition. The hydrogen adds here and the ethyl adds here. Ultimately, what happens is that this 1,4 addition, 1, 2, 3, 4 addition, that hydrogen kind of ends up there. So 3,4 addition, or conjugate addition, in the case of these alpha beta unsaturated compounds, is really 3,4 addition once you do everything. So here we have sort of a similar case, but slightly more complicated. So this starts out the same way. Again, I've chosen to do a symmetrical ketone. So the first thing that the second thing we're going to get is this compound. And so now again, we have this alpha beta unsaturated carbonyl, and it's going to react with the cuprate. And I picked this example for a reason. Cuprates, unlike regular alkyl halides, which are electrophiles, are not limited to being SN2 worthy substrates because they're not the substrate in an SN2 reaction. And so what will work here is primary alkyl groups, vinyl, aryl, any of those will work. So the cuprates are more versatile. What won't work is secondary or tertiary cuprates, and that's because those tend to do an elimination. It has nothing to do with an SN reaction, because that's not what's happening here. So now we're going to add our phenyl group, if we get the right implement. And we're going to add the phenyl group here. Not great atom economy with this this cuprate. Let me get this a little more accurate. And so we're initially going to get this compound because we didn't add acid yet. And now this species, has a second resonance contributor that looks like this. In other words, it's an enolate. And now we're going to do the reaction where the enolate acts as the nucleophile, and this alkylating entity is our familiar electrophile, and I'm going to push this down here. So there's our phenyl group. There's our CH3. And now we don't need any protonating agent because we don't need to add any hydrogens. The electrophile that we used here was the methyl iodide, and so that just gets there. And so what we've done here is we've alkylated the alpha position and the beta position. So these last three are kind of harder conjugate additions. So we can also get conjugate additions of enolates and related species to these alpha-beta unsaturated systems. And this is when things get probably as hard and weird as they get in this course in terms of making complicated things with lots of carbons. So the first step here is we're going to make the enolate of our diketone. And again, we've got the two carbonyl groups, 1,3 relative to each other. So this alpha position is alpha to both carbonyls, so we can make that with KOH. And then what's going to happen is this great big thing is going to do a conjugate addition. And it does a conjugate addition because this particular enolate is a weakly basic enolate. And that works because it is the enolate of a 1,3 dicarbonyl. A regular enolate would just add directly to the carbonyl because that would be a stronger base. So let's write this thing out. So I'm going to write the initial adduct that we get. So there's our enolate. So we have that species. And now we're going to protonate this and then do an enol ketotautomerization. And I'm just going to write all that out at once. And that gives us that as a final product. And we should check the product that we get from one of these so-called Michael additions should be a 1,5 dicarbonyl from a Michael. So we have 1, 2, 3, 4, 5. That's a good thing. And since this was the alpha carbon and it's alpha to both carbonyls, doesn't matter if we go 1, 2, 3, 4, 5, or what I just did. You're not going to go from one carbonyl from the enolate to the other because that's not the new compound that you made. So when you use these enolates of dicarbonyls, your product is going to end up having 3 carbonyls in it. 2 from the one that acted as the weakly basic enolate and 1 from the alpha-beta unsaturated system. So that's one thing we can do. We can do these Michael additions in order to do a conjugate addition. Another way to get a conjugate addition is by using this enamine synthesis. Sometimes it's called the Stork enamine synthesis because, yes, there's yet another person involved in this chapter whose name is associated with the reaction. So Michael, presumably that's the last name of somebody. We've got Gilman. Now we have Stork. And so let's look at what's going to happen here. So the first thing that happens is that we have a ketone carbonyl and a secondary amine. And what that does is it makes an enamine synthesis, hence the name Stork enamine synthesis. Sometimes these things make sense, sometimes they don't. And I've deliberately set up my carbonyl compound so that only one side of the ketone has alpha hydrogens because the regiochemistry in these is kind of complex. Incidentally, if anybody cares, R2NH is actually pretty often parole, but the Klein text chooses to write it this way. And remember with the enamine or imine formation that the pH has to be low enough to get the OH that comes from the carbonyl oxygen to leave in the mechanism, but not so acidic that it protonates the amine and makes it not a nucleophile. So again, this is a Michael adduct. Well, it's not a Michael adduct. It's Michael donor. That's what they call this. So not only does he get the reaction named after him, but he has all the reagents named after him too, assuming it's a man, which it probably is. So we have the Michael donor, and then this, believe it or not, is called the Michael acceptor. All nomenclature you don't have to know, even if your name happens to be Michael. And so what's going to happen here, let's go for a different color, is that this lone pair does this, and then this bond is going to go, whoops, over here to that, to that. All right. And this is a good time to make sure you count your carbons and get them straight. For some reason, it seems like when you stick these two things together, sometimes you end up with kind of, you're missing a bond, but we'll check that. So the result of this is going to look like this, whoops, and R2. So we get this iminium ion. There's our enolate. And then we're going to add this to our Michael acceptor, which has 4 carbons. Let's see. 1, 2, 3, 4. 1, 2, 3, 4. That's why I said count your carbons. Because the new bond is there. And the carbonyl is initially, let's draw what we get initially here. So that added here, so we have that. O minus. No, something bad happened here. What did I do wrong? I always do this. Except it's not that. It's this. So let's see, does that make sense? We made a new bond. We have 1, 2, 3, 4. And then that, yes, so that makes sense. So that's our initial adduct. And as I said, make sure you count your carbons. And so then what happens when we add the H3O plus, which I just gestured over and didn't really point out, when we add the H3O plus, that does a couple of things. The H3O plus here protonates the O minus. It catalyzes the enol to keto tautomerization. And it hydrolyzes this iminium ion to the carbonyl. So 3 things. And so the product that we're going to get out of this, which I'll write up here, hopefully fit in. So there was our enolate, and then we're going to go 1, 2, 3, 4. So that becomes a carbonyl, and I really apologize for that awful bond. Again, we should have added a 1, 2, 3, 4 carbon piece to this. And notice that again, just as we did before, what we get here is a 1, 2, 3, 4, 5 dicarbonyl. So from a Stork enamine synthesis, we also get a 1,5 dicarbonyl. Again, I thought I'd left myself all this room, but apparently I hadn't. And I'm not going to take the time to redraw it. So the final reaction starts out as a Michael addition, And we now know that Michael additions give you 1,5-dicarbonyls. Well, you may or may not remember from one of the earlier sections in this chapter that 1,5-dicarbonyls do an intramolecular aldol. So that's what's going to happen here. So let's go ahead and draw the initial thing that happens. So we're going to make this enolate, and that enolate is going to attack that carbon. So there's your enolate. So let's count our carbons. We should have added 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're good. Okay. And except we have that. Okay. And so we're going to protonate this thing. And that should give us our 1, 2, 3, 4, 5 dicarbonyl. And so this 1,5-dicarbonyl, with the motivation of heat, can now do an aldol. And so if we assess this as an aldol reaction, these two carbonyls are equivalent, right? Everybody can hopefully see that. So it wouldn't matter which of those carbonyls got involved in the reaction. So now if we evaluate this a little bit more, the most logical place to make an enolate is between the two carbonyls. But if we make the enolate there, the only thing it can do is make a ring that has 1, 2, 3, 4 carbonyls, which doesn't seem terribly likely. So a ring, a 4-membered ring, does not seem very likely. So even though, yes, that's the likelier enolate to make, the enolate that we're going to have to end up making is that enolate. And that enolate is going to attack one of those two equivalent carbonyls. It really does not matter which one. So I'll have it attack the lower one, and I'm also going to take this bond and put it up there. So if we have a 1,5-dicarbonyl, that's going to give us a 6-membered ring. So we've got that, and then we have, this is here, and then we've got that there, right? So again, from our aldol, we've made this beta hydroxy ketone. And when this is heated, it will do the full aldol condensation and dehydrate. And that will give us as a final product. So when this OH leaves, well, actually first it pulls off a beta hydrogen, and it could pull off that beta hydrogen or that beta hydrogen, not that beta hydrogen, because I very cleverly put a methyl group there in my reactant. And so it's going to be that one, because in an aldol condensation, you always make the double bond in conjugation to a carbonyl. So that is your final product. And again, this process of the Michael addition and then the aldol reaction of the resulting 1,5-dicarbonyl is known as a Robinson annulation. And I promise that I will not ask you to do a question where you have to work this backwards, although it's pretty logical to do. If you ever do have to do it, my recommendation is you do the retroaldol, and then you figure out what pieces you need to do